directly to the next presentation from Burkhard. So let me introduce Burkhard. Burkhard Ringlein is a predoctoral researcher in the Cloud and AI Systems Research Department of the IBM Research Laboratory in Zurich. And he's pursuing his PhD in cooperation with the Department of Computer Science and Computer Architecture of the Friedrich Alexander University in Erlangen, Nuremberg, Germany. As part of the Cloud FPGA project, he is focusing on distributed reconfigurable architectures in the context of high-performance computing and AI acceleration. And beside this, he is interested in designing compiler stacks for supporting heterogeneous computing platforms. So please, Burkhard, you may start with your presentation.
Yeah, thanks, Dionysius, for the kind introduction. I hope you can see my screen and audio is good.
Yes, everything is fine.
Great. Okay, hi everyone, and as you can see, I ask a question in this talk, and so somehow as a pre-word, I ask a question in this talk, and I do not intend to present a cooked solution for this question. Instead, I want to share some thoughts and to start a discussion in our community about the way we design our FPGA platforms and applications. But okay, let's start at the beginning. FPGAs are spreading in data centers and clouds, and that's why we are all here. So we don't need to discuss it. And I think everyone knows the examples on the right and on the left-hand side and we have heard from Microsoft today, we have heard from Inaxel today, we have heard from the Paderborn cluster today, and there are a lot of other academic or experimental setups. The consequences of this development are that the multi-user environment of these clouds constrains the used microarchitecture inside the FPGA. And typically, not all application developers want to deal with the I/O details of the specific boards. Hence, the vendor typically provide a platform and some templates or development kits for the FPGA design, as also presented today. So, very frequently, these platform development kits follow a well-known pattern, the shell role architecture, or board support package, as Tobias has called it. The design pattern splits the FPGA logic in two parts: the platform-specific part containing I/O or PCI Express, or the network IP cores are contained in the shell, and the application-specific part that I'll refer to as the role. The shell is controlled by the vendor, the role by the user or application developer. This design pattern offers various advantages, such as abstractions of I/O, different privilege levels, and the guaranteed integrity of the control path, and therefore improves the security of the platform. For example, the DDR4 memory, if it's part of the board, the memory connections are presented to the user as easy-to-use AXI4 buses, not as differential DDR signals. Additionally, the vendor can enforce via the shell that the user stays within her or his designated memory region, which is important if there are multiple roles or other attached memories to this FPGA. Consequently, the SRA design pattern is widely used, as you can see in the following examples. And since a lot of people speak about APIs, I call the SRA somehow the APIs of FPGA developers, because that's somehow the interface the app developer faces to design his application. So some examples are AWS on the left-hand side. I think you have all seen that. OC Axel or the OpenCAPI Snap framework here on the top right. Our Cloud FPGA in Zurich is somehow depicted here on the lower right-hand side. And there are, as I said earlier, a lot of other examples like the Alveo cards itself, the Microsoft project as far as we know it, and some other cloud projects. But so we can see that a lot of researchers and engineers came up with relatively similar solutions for a similar problem. But every vendor provides a different interface, and these interfaces are incompatible to each other. At the time where I started to research FPGAs in the cloud, as young and maybe naive PhD student, I found myself somehow in a situation that was similar like the picture on the right-hand side. There were a lot of powerful efforts which wanted to convince me about their way and their only way to the cloud, so how to do it correctly. I was left with the impression that actually everyone wants to do the same, but with different directions. And to me, this appears like another problem in the way to the clouds for FPGAs. Okay, why is this actually a problem that we have somehow competition between different approaches. If we consider the typical way of developing a new FPGA application, we have somehow 8 steps, more or less. First, we have an idea and motivate ourselves that the cost is worth the effort, the benefits is worth the effort to go with this application to the FPGA. Yeah, and then usually you start developing this application in HLS or HDL or some other language and verify it. And after this kernel is ready, you care about how this gets on our target card or the target platform. And we've seen earlier a lot of diversity of this in different environments. So after that, you simulate the complete role or the complete application or emulate it in the final environment. And after this step, you can deploy it on real hardware. This, I guess, also resonates what we have seen in earlier presentations. The problem is now, if you want to deploy the same kernel or the same application on another platform, only the first steps are reusable, and the integration in the target environment needs to be redone every time. So this view is maybe a little bit simplistic or a little bit naive, because FPGA applications actually are tightly coupled to the interfaces, because that's why we want to use FPGAs, right? We don't want to convert types within the FPGA, so to convert the bus width or so. If you want to have high throughput and low latency, we need to consider the interface at design time. So FPGA applications are barely interface agnostic, and consequently they depend on the API of the shell, which leads to this described situation that we have a limited reusability and portability of FPGA applications. And I think that's a problem. So what would be a better solution? Or actually, what are the reasons for this problem? Actually, FPGA app developers have a lot of good reasons to change the used FPGA platform. For example, elasticity or scalability of cloud solutions. We have heard by Chris just something about hybrid clouds and so on. Or simply we want to switch to a better platform, and so, yeah, other business decisions. Reusability would greatly accelerate the change of platforms and would also accelerate the growth of the ecosystem, because I guess also more businesses are willing to invest in FPGAs if they would know that they can seamlessly leverage future technologies or future platforms. So we knew, and to keep pace with the current life cycles, we need reusable FPGA designs. And if we would have portable roles or portable applications, we can simply switch to a new platform and therefore leverage new technologies. Also, like Derek said in his talk about compile times and so on. Yeah, I think we as FPGA community can learn from history how to overcome this trap and not redo the mistake of others. Because once upon a time in the 1970s and 80s, there existed a lot of different operating systems that were incompatible to each other as well. Additionally, not every operating system did run on every CPU system. This situation led to the formulation of POSIX, the Portable Operating System Interface, with the formal name IEEE Standard 1003, and the first version was released in 1988. The idea is to have a common interface for application and tools, and therefore a POSIX compliant application can be recompiled at any platform without code changes. Consequently, portable applications could be developed without big efforts for the application developer. POSIX accelerated the development of applications because the developers no longer had to worry about platforms. But also, POSIX also made the life of administrators easier, because a lot of administration tools are also covered by POSIX and consequently behave the same way on all platforms. Hence, POSIX enables the equation code once, run everywhere if you have a compiler. As I said, I think we can learn from this historic development, and therefore I will present some more details about POSIX. As core idea, POSIX defines application programming interfaces or APIs and their corresponding data structures for the interaction with the operating system kernel. If you have never done it and you are right now sitting in front of a Mac or Linux or a compatible shell in Windows, you can type this command man3p-zen2, and this will open the POSIX programmer's manual as depicted here on the right-hand side. This manual page contains all information how any application, for example, the Zoom client in front of which you are currently sitting, or the browser, can tell the operating system to send data via a network connection. Consequently, any program that was written after 1988 and that applies the POSIX API and is written in a programming language that has a compiler for the target platform can be ported to any POSIX compliant platform without any code changes. Furthermore, POSIX also defines which comments invokes in compiler to compile the application on the target platform. In a nutshell, POSIX makes the life easier for all, for operating system developers, because they knew the interface that a lot of applications use, for system administrators, because at the higher level, every operating system started to behave the same way, and finally for application developers, because they were able to develop a multi-platform application with a single code base. But POSIX didn't limit one of them. POSIX just provided the interface and not the implementation of the operating system kernel or the compilers. However, POSIX ensured that all these tools, applications, and platforms stay compatible to each other, just by providing the standard and some PDF files, so to speak. So the question is now, can we do this for FPGAs too? Can we bring design once, run everywhere to FPGAs? Is there a way to enable portability on FPGA platforms so that FPGA developers can execute the application on multiple platforms and platform developers have a number of applications as benchmarks available? We as the FPGA team here in Zurich think the answer is yes, and we want to discuss our proposal to solve this with you, the openRole proposal. Actually, the current situation as starting point isn't so bad. As said earlier, a large number of FPGA platform vendors have already found similar solutions. Usually, FPGA apps aren't existing in empty space. They are part of a more or less complex communication schema with other FPGAs or CPUs. If we analyze all the earlier mentioned shell role architecture from this perspective, we find some general patterns. Every role is controlled by some configuration and control registers or signals like start and stop or node ID or virtual I/O pins. Besides this, every shell role architecture uses one or two of the following communication channels: address-based communications, especially for PCI Express attached or memory synchronized FPGAs, and stream-based communications for network attached FPGAs or some fabric abstractions. Every fabric can be abstracted by these two communication types. The synchronization between these interfaces and the other devices, for example, CPU, is up to the magic protocol of this platform, as sketched here on the left-hand side. In my experience, most application developers don't care how the data is synchronized between FPGAs and CPUs. Application developers don't care if there's a PCI Express, Ethernet, or carrier pigeon in between, as long as bandwidth and latency are sufficient for the needs of the application. That's why I think we should describe a standard interface on this level and leave the details of the magic, or leave the details of the synchronization to the magic of the platform. That way we achieve both portability of the application and competition of platforms. Yeah, so, but what do these common concepts bring? I think if we handle it in a right way, it allows the compilation or synthesis of any role for any compliant platform. As it here depicted on the right-hand side, the openRole interface is only relevant before synthesis. So if you put your developed HDL, MLS or HLS app together with a shell and want to synthesize it for a specific platform, any optimization offered by the vendor comes afterwards. And of course, the concept can also be extended to binary versions, so to have an application binary interface if you think about partial configuration. So in order to work, the shell just needs to support the openRole API, and the user can port his role to another platform with just a single click. As I said earlier, the idea is not new, and the default, it's somehow the default in the software world. So who would buy a new laptop if you know he would need to rewrite every software for this laptop? So that's somehow how it works every time in the software world, where you can develop your app and use the system calls or a library that abstracts the system calls and combine this to your operating system, and the compiler can handle it. So if we do so, we can enable portable FPGA designs. We just have to agree on a common interface. And to be clear, it is not about porting software to FPGAs. openRole is purely about FPGA to FPGA portability. So not to be locked with one specific platform. So to help the discussion, I will now present some more concrete ideas for this interface definition. The FPGA side of the interface should solely base on AXI version 4. To achieve the goal of portability without any code change, there should be only one defined interface. Template parameters, for example, for bus, width, or data type should be possible to achieve with AXI interconnects. That way, it is possible that every specific shell fits to every specific role without trouble caused by template parameters. Indeed, this would maybe limit the bandwidth or a specific combination of roles and shell, but at this point, I think we should enable portability for all and leave the optimization of specific use cases to these users. And following this approach, the AXI interconnect can also be automatically inserted by a compiler. And I guess here we are at the same trade-off that Derek mentioned with 100 times speed up and 3 years of development, or maybe 10 times speed up and a little bit lower time of development. The interface should include the following AXI buses. The earlier mentioned address-based and stream-based communication, and it should contain always both, even if one type would be emulated by the shell. For example, in case of stream-based communication, it could be emulated via PCI Express. I think it's still better that this is done by the shell or if it's done by the user. Additionally, we need control registers. The most general and lightweight interface for registers configurations would be AXI4 Lite. Furthermore, we think that also the delivery of virtual interrupts to the role makes sense. For example, to notify the applications that a memory transfer is finished. But this is, of course, up to discussion. A sketch of how we image in this interface and a snippet of a possible VHDL definition is given here on the left-hand side. But of course, this is just an example, and the interface could also be defined at any other level, higher language or lower languages. Besides portability, the use of only AXI-based interfaces has two more key advantages. First, we already know at the time of the interface definition how the debug probes for all future applications will look, so we can make debug easier. Second, we know the bus definitions, we can relatively easily integrate performance profiles at the shell side. Hence, using the standardized interface has also an easier debugging and profiling for the user as a consequence. Now let's switch the side and look at the CPU part. As mentioned earlier, there's always a CPU involved in FPGA applications, so we should specify this part of the platform too. Hence, we need functions that mirror the interface at the FPGA side. For example, we need a way to write to the configuration register of the role and to retrieve a status from the application. Next, we need, of course, the data path and have, again, both types of communication. Write and read functions for address-based communication and send and receive for stream-based communication, just as a proposal. A brief sketch is given here on the right-hand side along with the function signatures of the mentioned APIs. In general, there could be multiple roles part of one application, and that we need some kind of identify the roles, and therefore we propose a unique ID to identify the roles, and this ID should be, of course, work for all type of fabric. So we should not take PCI Express addresses or IP addresses. So at this point, we should abstract this away. Yeah, to conclude, hopefully in time, as a summary, we want to accelerate the development of FPGAs in cloud and data centers. And therefore, we should enable design once and run everywhere for heterogeneous platforms. openRole is a proposal to achieve this and escape the deadly situation of disparate platform architectures. openRole is not an implementation, and it assumes the presence of compilation tools. openRole is also not a programming model. It is about portable FPGA designs. Consequently, the interface should be published only with header files, VHDL entities, and further definition in PDFs. But with this standardized interface, we can achieve true portability of FPGA applications. Therefore, FPGA app developers can execute their application on multiple platforms, and furthermore, platform developers can trust that there will be an application that can be executed on their platform. If you are interested in shaping and designing openRole, or you would do it completely different, you are of course very welcome to contact us or discuss it later. And with that, thank you, and I'm looking forward to the discussion.
Thank you very much. Thank you very much. So we will move on the next presentation.